Hey everyone, and welcome to today's Explainer. We're going to zero in on an absolutely critical piece of your Spring Boot architecture, and that is how AI Fabric manages secure, multi-turn conversational memory. Look, if you've been working with large language models at all lately, you know that keeping track of context is literally everything. But the real question is, where exactly should that context live? Well, today we are going to break down exactly how AI Fabric keeps that state safely locked down in the backend.
So let's just jump right in. Why does your backend, and not the user's browser, have to own the conversation history? Sure, the browser displays a nice chat UI, but it absolutely cannot be the source of truth for what was actually said, or which record was selected, or which write operation is just waiting for confirmation. That responsibility, it belongs 100% to your Spring Boot backend.
So here is our roadmap for the journey of a follow-up. We'll be walking through the problem with follow-ups, activating backend memory, enrichment and bounds, drafts versus pending actions, recording and expirations, and finally, ownership and isolation.
Starting with Section 1, the problem with follow-ups, and frankly, the danger of relying on client-side transcripts.
To really get why AI Fabric handles things this way, we have to look at the dangers of trusting client-side transcripts. Picture a totally standard chat sequence for a second. A user asks, "Why is ticket T1042 unresolved?" Then they say, "Escalate it." And finally, they just say, "Yes." Now ask yourself, how on earth does your system interpret the word yes in total isolation? The phrase escalate it doesn't identify a ticket by itself, right? And the word yes certainly doesn't identify what the user actually just approved. Without authoritative backend context from that exact specific conversation, these follow-ups are completely ambiguous. And honestly, they're potentially dangerous to execute.
So here is where the architecture really diverges. Think about the naive approach. It's a bloated, insecure request where the browser just sends the entire chat history back to the server on every single turn. That practically invites manipulated transcripts to rewrite history. Now compare that to the extremely lean AI Fabric approach. The client simply sends one single new message, like the word yes, along with a stable conversation ID. From there, the server derives the current owner from their authenticated identity and constructs the orchestration context natively. It's so much cleaner. Moving on to Section 2, activating backend conversation memory and fulfilling those necessary contracts. Turning on chat memory in AI Fabric, it's a real architectural commitment. It is significantly more involved than just, flipping a prompt toggle. It requires you to fulfill very specific backend contracts. First off, you've got to add the module. Second, you have to supply a chat session storage provider. So, for example, using the default database storage with JPA. And third, you must provide the crucial chat session access control policy. In fact, if you enable the chat feature without a storage provider, the framework's validator is actually going to fail your application right at startup. And the definition of this chat session access control policy is absolutely vital. I really want to emphasize this point. A simple policy grant is just not enough here. The AI Fabric service actually invokes this policy to verify that the stored session truly belongs to the current authenticated owner, and it does this before exposing any history whatsoever. If an owner is mismatched or blank, loading and recording will categorically reject it, no exceptions.
Let's look at Section 3, enrichment and bounded limits. Basically, managing prompt limits.
Before the LLM even catches a glimpse of the request, AI Fabric has to inject this trusted, verified memory right into the orchestration pipeline. This all goes down during the conversation enrichment step, which runs right inside your request pipeline. It executes after the access control we just talked about, but before intent handling. It reaches out to the chat session service for recent messages, and then adds those role-aware messages, properly split into user and assistant roles, of course, straight into the pipeline context. It also seeds bounded working set targets, which effectively brings recently resolved records right back into scope for the current turn. Now, think about the number 10. The default sliding window limit in AI Fabric is exactly that, just 10 turns. This is hard proof that memory is intentionally bounded. You're not meant to just send every single historical token forever. By having the backend control this window, you prevent stale context from confusing the model, and you really rein in those token costs. And alongside that turn limit is a character cap, which defaults to 8,000 characters. But the real game changer here is how it enforces this. AI Fabric doesn't just arbitrarily chop a sentence in half just to squeeze into a prompt limit, no way. The system strategically drops the oldest, whole messages until the history actually fits within the bounds. This ensures your LLM never receives weird, confusing, partial substrings from early in the conversation. All right, Section 4,
drafts versus pending actions, or incomplete versus ready. Let's shift gears a bit and focus on governed actions. How does AI Fabric handle an intent that's incomplete versus a command that is fully ready to execute? Well, on one hand, we have an action draft. This happens when a selected action is missing some required user information. It's basically an incomplete proposal that still needs clarification. On the other hand, we have a pending action, and this is a completely different beast. A pending action has been fully validated, it's authorized by your domain rules, and it is now sitting safely in your backend session metadata, literally just awaiting the word yes. Keeping these two states strictly separate prevents a user from accidentally approving a proposal that was never even fully formed.
And here's exactly how that approval goes down. The confirmation resolution step loads up the session metadata for the current conversation. If the user gives a positive yes, this step resolves the pending action and consumes it directly from the backend state. And because that state is essentially popped off the stack, if a duplicate yes is sent a second later, it's going to fail. The proposal is already gone. This is exactly what protects your entire system from accidental duplicate executions.
Moving into Section 5, Recording and Expiration Strategies. This is all about managing state lifetimes.
We're at the tail end of the pipeline now, where we actually save the sanitized outcome. The conversation recording step runs very late in the pipeline, long after the response has been sanitized. It records both the current user query and the assistance message. Crucially, if you happen to have the PII service available, this step redacts sensitive information from the query again before persisting it. Oh, and it completely respects the never persist mode. If you tag a request with never persist, it bypasses this storage entirely. That means your transient, highly sensitive workflows never ever enter your chat memory. Because let's face it, memory isn't permanent. Prompt history is bounded by the turn and character limits we just discussed. Pinned targets, like, say, a selected support ticket, have a default reuse window of just 3 turns before they naturally fall out of scope. And those pending confirmations, they have a strict built-in timeout of exactly 5 minutes. Conversation state has several distinct lifetimes, and they're all custom designed to keep the context relevant and, above all, secure.
And finally, Section 6, Proving Ownership and Isolation by Enforcing Strong Boundaries.
We have to actually demand proof that this architecture works. This is exactly what your testing matrix should look like. You need to prove continuity and isolation. If a totally new conversation ID is sent, the prior context and any pending actions absolutely must be absent. If a different owner tries to read the session, the backend has to return an access denied error before any history is exposed. Because listen, a passing LLM response on your screen, that is not proof of isolation if your browser just secretly resent the transcript. The enforcement has to happen at the backend boundaries.
So ultimately, who owns what here? The core philosophy is actually really simple. The client only owns the current message and the current UI attachments. That is it. The Spring Boot backend, through AI Fabric chat session storage, owns the authoritative conversation history, the metadata, the drafts, and the pending actions. Identity and authorization stay firmly in the hands of your application security layer.
So, I'm going to leave you with this to think about. If the browser just sends the word yes, does your backend actually know what it's approving? With a naive client-side transcript, the answer is a hard no. But with AI Fabric's backend-owned memory, your system knows exactly what that yes means, exactly who said it, and it knows for a fact that the context hasn't been tampered with. It's a massive foundational shift in how we build enterprise AI workflows. Thanks so much for joining me on this explainer. I really can't wait to dive into our next architecture breakdown with you.